right, here let's pick up where we left off in section 7.4, but this time let's look at a function of three variables. So here we have w equals x times e to the x times y plus 2z. So w is a function that takes in three inputs and produces exactly one output, and we want to find wx, wy, and wz. Now functions of three variables, they behave the exact same way as functions of two variables. When we're taking the partial derivative of w with respect to x, we hold y and z constant, and we're taking the derivative with respect to y, we treat x and z like constants, and we're taking the derivative with respect to z, we treat x and y like constants. So let's take a look and calculate wx. Again, here we're going to have to use product rule, no ifs, ands, or buts about it, because we have the function x and the function e to the xy plus 2z multiplied together. So we're going to use LDR plus RDL. So let's write down what all of those are. L is the left function, is just x. R is the right function, which is e to the xy plus 2z. If L is x, then DL is just 1. And if R is this complicated thing, then dr, with respect to x, is the derivative of the inside times the derivative of the outside, is e to the xy plus 2z times, and now the derivative of this top part here, the derivative of x times y plus 2z. Well, the 2z is just a constant, so we don't worry about that. All we have to worry about is the derivative of x times y, and because y is being treated like a constant, we just get a y. So writing all that together, LDR plus RDL, we get x times e to the xy plus 2z times y, plus r, which is e to the xy plus 2z, dl, which is just 1. I won't even bother writing it down. Here, I suppose we could simplify this a little bit further if we wrote e to the xy plus 2z times xy plus 1, just factoring the e to the xy plus 2z out of the left and right. But that's wx. The easier ones are wy and wz. So wy, remember the original function is x times e to the xy plus 2z, and we're treating x like a constant here, so the derivative with respect to y is just x times the derivative with respect to y of e to the xy plus 2z. And here we have to use chain rule, but we end up with x times the derivative of the outside is e to the xy plus 2z, and the derivative of the inside, the derivative of x times y plus 2z, is just x. So our final answer will be x squared e to the xy plus 2z. And lastly, wz is just, again, because x is being treated like a constant, we'll end up with x times the partial with respect to z, e to the xy plus 2z, and again here we have to use chain rule, and what we end up with is x times e to the xy plus 2z times 2, which simplifies down to be 2x e to the xy plus 2z. From here, I want to take a quick note about higher order partial derivatives, namely fxx, fxy, fyx, and fyy. They act exactly how you think they should, and they are exactly what you think they are. Fxx is just the partial derivative with respect to x of fx. Fxy is the partial derivative with respect to y of fx. Fyx is the partial derivative with respect to x of fy. And fyy is the partial derivative with respect to y of fy. So let's take a look at an example. We want to find the second partial derivative of f of xy equals 3xy squared minus 2y plus 5x squared y squared. And we want to determine fxy of minus 1, 2. In order to find second partial derivatives, we have to find the first partial derivatives. So let's do that first. We want to find fx, we treat y like a constant. The derivative of 3xy squared, because we're treating y like a constant, is just 3y squared, minus the derivative of 2y is just 0, because 2y is a constant, plus the derivative of 5x squared y squared. Well, we bring the exponent down, we get 2 times the constant, 5y squared, times x. So this is our fx, which I guess we can simplify a little bit to be 3y squared plus 10y squared x. And if we want to calculate fy, well, now we're holding x as a constant. The derivative of 3xy squared, 3x is a constant, so we bring the exponent down, multiply by the constant 3x times y. minus the derivative of 2y with respect to y is just 2, plus 5x squared times y squared. Now we're treating 5x squared as our constant. We bring the 2 down, and we get 2 times 5x squared times y, which simplifies a little bit to be 6xy minus 2 plus 10x squared y. So now we have fx and fy, and now we can find fxx, fxy, fyx, and fyy. So let's start with fxx. fxx, we're going to take fx, which remember is 3y squared plus 10y squared x, and we're going to take its derivative with respect to x. So we hold y as a constant. The derivative of 3y squared with respect to x is just 0, plus the derivative of 10y squared x with respect to x is just 10y squared. So fxx is just 10y squared. Now that we found fxx, our goal is to find fxy. And the way we do that is we take fx, which we found, and we take its derivative with respect to y. So the derivative of 3y squared with respect to y is just 6y, plus, and then the derivative of 10y squared with respect to y, we treat 10x as a constant. We get 2 times 10x times y. So this simplifies down to be 6y plus 20x times y. All right, and now we can find fyx. So we take fy, which we found to be 6xy minus 2 plus 10x squared y, and we take its derivative with respect to x. So the derivative of 6xy with respect to x is just 6y. The derivative of negative 2 with respect to x is just 0, plus the derivative of 10x squared with respect to x. We treat 10y as a constant, so we bring the exponent of the x down, so we get 2 times 10y times x, which simplifies down to be 6y plus 20y times x. Now, you may notice that fxy and fyx are the same. They're both 6y plus 20xy, or I guess 20yx down here, but those are the same thing. And that's because it always works that way. fxy and fyx are always the same, so if you're ever tasked with finding, the 4 second-order derivatives, you can quit at just 3. All right, lastly, let's find fyy. So that's the derivative of fy with respect to y. So again, fy was 6xy minus 2 plus 10x squared y. We're going to take its derivative with respect to y. The derivative of 6xy with respect to y is 6x minus 2, but the derivative of 2 with respect to y is just 0, plus the derivative of 10x squared y with respect to y. We just get plus 10x squared. Now that we found all of these, the last part of the question was evaluate fxy at the point negative 1, 2. So fxy, again, is 6y plus 20xy, evaluating the point negative 1, 2. So that means we're going to plug negative 1 in for x and 2 in for y. And we're doing that because we're given fxy, and we're evaluating at the point negative 1, 2. X always comes first, y comes second. So we have 6 times y is 2, plus 20 times minus 1 times y is 2. So we get 12 plus minus 40, which that works out to be minus 28. A quick note about second-order partial derivatives is that the number of higher-order derivatives increases exponentially. A function of 2 variables has 4 second partial derivatives and 8 third partial derivatives, etc. And a function of 3 variables has 9 second partial derivatives and 27 third partial derivatives. So buckle up for this last question. Find the second partial derivatives of f of x, y, z equals y times e to the x plus x ln z. The fact that this is a function of 3 variables means there will be 9 second partial derivatives. But before we can find those, we have to find the 3 first partial derivatives. fx, the derivative with respect to x, we treat y like a constant. So the derivative of y times e to the x is just y e to the x, plus the derivative of x times natural log of z. Well, remember, natural log of z is just a constant, so the derivative of a constant times x is just that constant. So fx is y e to the x plus ln z. Fy, We treat everything that's not y like a constant, so we treat x and z like a constant. So y times e to the x, well now e to the x is just a constant because e to any constant number is just a constant. So y times a constant, we take the derivative, we just get that constant. So we have e to the x plus, and then x times natural log of z. Both x and z we're treating like constants, so x natural log of z is a constant, so its derivative is 0. So that means we're done with that. We can turn our attention to f of z. Or not f of z, sorry, I should say f sub z. I say sub z because we write z as a little subscript. The derivative of f with respect to z, well, y times e to the x, that's a constant, so we don't care about it, plus x times the natural log of z. So now x is a constant. The derivative of x times natural log of z with respect to z is the same as x times the partial derivative with respect to z of the natural log of z, which is going to be x times 1 over z. So we end up with x over z. So fx is y e to the x plus ln z, fy is e to the x, and f of z, or f sub z, is x divided by z. With that in mind, let's focus on the 9 second-order derivatives. fxx. Okay, so we're taking fx and taking its derivative with respect to x. So natural log of z now is just a constant. We don't worry about it. Its derivative is 0, so the only thing we have to worry about is y times e to the x. But because y is a constant, the derivative of a constant times e to the x is just that constant times e to the x. fxy. We're taking fx and finding its derivative with respect to y. ln z is a constant, so it goes away to 0. And then the derivative of y times e to the x, well, that's y times a constant, so we just get that constant. Now f of x is z. So we take fx and take its derivative with respect to z. Y times e to the x is a constant, so we can basically ignore it. The derivative of natural log of z with respect to z is 1 over z. fyx, well, that's the same as fxy, like we talked about earlier, so it's just e to the x. fyy, well, here we have fy as e to the x. We're taking its derivative with respect to y, so e to the x is a constant, so we get 0. fyz, by similar reasoning to fyy, fyz will be 0, because e to the x is a constant with respect to z. fzx, well, that's the same as fxz, so it's 1 over z. fyz, it's the same, fzy, well, that's the same as fyz, so it's 0. And lastly, fzz. So we're taking the derivative of x over z with respect to z, and that'll get us minus x over z squared.